To understand why Apophis captured the imagination of scientists and the public alike, it helps to start with how it first entered our story, not as a myth, but as a few faint dots of light on a telescope image. In June 2004, a team of astronomers using a telescope at Kitt Peak National Observatory in Arizona spotted a moving object against the background of fixed stars. At first, it was just another entry in a long list of newly discovered near-Earth objects. They gave it a temporary name, as is customary, 2004 MN4. Nothing about that label sounds dramatic or dangerous. It's just an alphanumeric code, a placeholder until astronomers can collect enough data to calculate a reliable orbit and assign a permanent number and name. But over the following months, as more observations were collected and the orbit became better defined, it turned out that 2004 MN4 was anything but ordinary. It wasn't a distant rock that would quietly loop around the sun, far from our concern. It was an asteroid on a path that regularly crossed Earth's orbit, a *** near-Earth asteroid ***, or NE, and one that would come unusually close to us in the year 2029. Near-Earth asteroids are not rare, thousands are known, but what made this one stand out was how close and how uncertain that 2029 approach appeared to be. When astronomers first ran the numbers on its orbit based on the limited data available, they got a startling result. There was a roughly 1 in 37 chance, about 7%, that this asteroid could actually hit Earth on April 13, 2029. To put that in human terms, imagine being told that a jumbo jet has a 1 in 37 chance of crashing. You'd pay attention for asteroid impact probabilities, which are usually vanishingly small. 1 in 37 is enormous. To communicate impact risk, scientists use a measure called the Torino scale, which runs from 0, no risk, to 10, a certain civilization-changing impact. Most asteroids that cross Earth's path sit comfortably at Torino 0. Occasionally, one will bump up to 1, meaning a routine discovery that bears watching but almost certainly poses no threat. Apophis, still known as 2004 MN4 at the time, reached Torino scale 4, the highest rating any asteroid has ever received during the time we've had this system. Level 4 means a close encounter with a 1% or greater chance of a collision capable of causing regional devastation. That language is carefully chosen, and it is serious. The press noticed. Headlines began to talk about a doomsday asteroid. Scientists, usually calm by training, were animated, but in a different way. For them, Apophis was a kind of stress test for our entire system of finding, tracking, and evaluating asteroid threats. Could we collect enough data, quickly enough, to know whether this object was a genuine danger? Could we model its motion with sufficient precision, taking into account not only gravity, but also more subtle forces? And what would it mean for the future of planetary defense if we could, or couldn't? As the significance of this object became clear, it also became clear that the bland label 2004 MN4 didn't capture its character. When an asteroid's orbit is well established, it receives a permanent number and may be given a name. This one was designated ** 99942 Apophis **. The name was not chosen at random. Apophis is a Greek form of ***, Apep ***, the ancient Egyptian god, or more accurately demon, of chaos. In Egyptian mythology, Apep is a giant serpent that attacks the solar bark of Ra, the sun god, every night, trying to plunge the world into darkness. Each dawn Ra is victorious again, but the battle never ends. There was another, more modern layer to the name. Fans of the science fiction series ** Stargate SG-1 * may recall that one of the show's main villains is also named Apophis, an alien tyrant masquerading as a god. Several of the discoverers were aware of this, the double meaning, mythic chaos and pop. culture villain, gave the name a certain flair. Naming a potentially hazardous asteroid after a god of chaos might seem like tempting fate, but it also did something important. It captured public attention in a way that strings of numbers never can. Apophis became a character in our story, not just a day to point. What physically is this god of chaos? Apophis is an asteroid roughly 340 meters across. Imagine a mountain of rock the size of a large sports stadium or 3 football fields laid end to end. That may not sound like much compared to a planet, but it's enormous on the human scale. For comparison, the object that exploded over Chelyabinsk, Russia, in 2013 was about 20 meters across. Even that small space rock shattered windows in 6 cities and injured over 1,000 people with flying glass and shock waves. The 1908 Tunguska event in Siberia, which flattened some 2.0 square kilometers of forest, is thought to have been caused by an object in the 50-60 meter range. Apophis is several times larger than Tunguska's culprit and vastly larger than the Chelyabinsk body. Depending on its exact composition and density, an impact by Apophis would release energy on the order of hundreds to over 1,000 megatons of TNT. That's tens of thousands of times the energy of the Hiroshima bomb. Such an impact would not be global extinction level. It wouldn't wipe out all life on Earth, but it would cause devastating regional damage, obliterating entire metropolitan areas or triggering tsunamis if it struck an ocean. In other words, it's exactly the scale of object that planetary defense experts worry about most. Big enough to do enormous damage, small enough that we're likely to discover many of them only in recent decades. From the moment its unusual risk became apparent, Apophis stood out as a wake-up call. It forced the scientific community to sharpen tools that had been developing in a more abstract way. Suddenly, what if became we need to know, and soon. Astronomers scrambled to find more observations of the asteroid, not only by pointing telescopes at it in real time, but also by searching through archival images taken years earlier, in the hope that Apophis might have wandered into someone's field of view before it had a name. These earlier sightings, called precovery observations, are gold for orbit calculations. The longer the time span over which you've seen an object move, the more precisely you can predict its future path. More data gradually narrowed the uncertainties in Apophis's orbit. As the mathematical cloud of its possible future positions shrank, the 2029 impact probability fell. By late 2004 and early 2005, new radar observations from facilities such as Arecibo and Goldstone helped tie down its trajectory even more tightly. Radar lets us measure an asteroid's distance and velocity with exquisite precision, far beyond what optical images alone can do. With those measurements, the 2029 impact scenario finally dropped to 0 probability. The god of chaos, at least on that date, would miss us. But even as the immediate danger faded, something else became clear. We had been lucky that this particular asteroid had been discovered early enough, and that enough infrastructure existed to track it. Apophis became a poster child for why comprehensive sky surveys, robust data analysis systems, and international cooperation were essential. Its story was one of the catalysts that contributed to the eventual establishment and strengthening of formal planetary defense efforts, such as NASA's Planetary Defense Coordination Office, dedicated to finding and tracking potentially hazardous objects and coordinating any future response. So Apophis is unique in several intertwined ways. It is a near-Earth asteroid of substantial size that came, for a period of time, uncomfortably close to being a real impact threat in our lifetimes. It is a potentially hazardous asteroid by definition, because its orbit brings it within 0 0.05 astronomical units of Earth's orbit, and it is large enough, over 140 meters in diameter, to cause significant damage if it ever struck. It has a name and a mythological backstory that resonate with its early reputation. And it arrived at a particular moment in our technological and scientific development when we had just enough capability to detect and analyze it, but not yet the mature planetary defense framework that we are now building. It also symbolizes something deeper about how science interacts with uncertainty and fear. At first, Apophis represented the unknown, a threatening calculation on a whiteboard, a small but not negligible chance that we might be hit by something our species had never before been able to predict. That uncertainty generated anxiety and sensational headlines, but it also pushed the scientific community to do what it does best: gather more data, refine models, question assumptions, and update conclusions as the evidence improved. In that process, Apophis transformed from a symbol of potential catastrophe into a case study in how well, given the right tools, we can read the subtle dynamics of our solar system. Even its mythological name, God of Chaos, takes on a different meaning in that light. In the ancient Egyptian worldview, Apep's nightly attack on the sun was a reminder that chaos is always possible, that the world's order cannot be taken for granted. But the story also says that Ra, the sun god, triumphs each dawn. In a way, Apophis the asteroid carries a similar dual lesson. It reminds us that the universe is not tailored for our safety. There really are large rocks out there on intersecting courses with our planet. Yet it also shows us that, with careful observation and understanding, we can take what looks like chaos and reveal an underlying order. We can turn "we might be hit" into "we know we will not be hit, at least for the next century." So when we say Apophis is unique, we're not only talking about numbers. Its 340-meter size, its 2029 close approach, or its classification as an S-type stony asteroid. We're also talking about its role as a turning point. It is the first asteroid that made the global community collectively pause and ask, in a serious, practical way, are we ready as a civilization to deal with this kind of threat? That question, raised by a faint moving speck of light in a kit peak image, is what elevates Apophis from just another entry in a catalog to a central character in the emerging science of planetary defense. On the evening of April 13th, 2029, our planet will have a visitor unlike anything modern society has ever watched in real time. For once, the drama of near-Earth objects will not be confined to scientists' calculations or abstract probabilities in a database. Instead, a mountain of rock hundreds of meters wide will sweep past our world, close enough that millions of people will be able to step outside, look up, and see it with their own eyes. That visitor is Apophis, and the circumstances of its 2029 flyby are what make this event scientifically extraordinary. To appreciate just how unusual this encounter is, it helps to talk about distance in concrete terms. At its closest approach, Apophis will pass at an altitude of roughly 1 to 32,000 kilometers above Earth's surface. The Moon, by comparison, is about 384,000 kilometers away. That means Apophis will be roughly 10 times closer to us than the Moon is. Communications satellites in geostationary orbit sit at about 35,800 kilometers above Earth, so Apophis will actually dive inside the ring of many of our own satellites. In the language of everyday life, it is as if a fast, moving truck were to roar through a narrow alley lined with parked cars without hitting any of them. Events like this are not entirely unheard of if you include very small objects. Tiny asteroids a few meters across pass between Earth and the Moon quite frequently. Some even skim the atmosphere and produce bright fireballs. But Apophis is not tiny, At about 340 meters across, it is in a completely different category. We know of no instance in the era of telescopes and space technology when an object of this size has come so close to Earth while we were aware of it long in advance, tracking it, preparing to observe it in detail. That combination, its size, the closeness of its approach, and our preparedness, is what makes 2029 uniquely important. The human experience of this fly will be remarkable. From parts of Europe, Africa, and Asia, Apophis will be visible to the unaided eye as a point of light moving steadily against the background stars. At its brightest, it is expected to reach about magnitude 3 on the astronomical brightness scale. That is dimmer than the brightest stars, but easily within the range of what most people can see from reasonably dark locations. What will set it apart is its motion. Unlike a star, which appears fixed, Apophis will drift noticeably across the sky over the course of minutes, like a slow-moving satellite, but much farther away and far more massive. For many people, this will be the first time they knowingly see an asteroid with their own eyes, and that alone has enormous power to make an abstract scientific topic feel real. From the scientific point of view, Apophis's 2029 flyby is a once-in-a-lifetime natural experiment. Earth's gravity will act on the asteroid like a powerful, precisely directed hand, altering its path around the Sun. Before the encounter, Apophis takes less than a year to complete one orbit of the Sun. After it passes us, its orbital period will lengthen to about 1-2 years. That change may sound small, but it is a dramatic demonstration of how close planetary encounters can reshape the architecture of the solar system over time. This is the same gravitational slingshot principle that spacecraft use to gain speed or change course by flying past planets. With Apophis, we get to watch that effect operate naturally on a sizable asteroid in our own cosmic backyard. Beyond simply bending its trajectory, Earth's gravity will also tug on Apophis's internal structure and spin. Asteroids are not always solid monoliths. Many are thought to be rubble piles, loose agglomerations of rock fragments and dust held together mostly by their own gravity. When such a body passes close to a planet, differences in gravitational pull from one side to the other, the so-called tidal forces, can flex it, shake it, and in some cases even tear it apart. Apophis will not come close enough to be ripped to pieces, but it will come close enough that tidal forces are expected to matter. Models suggest its rotation could change. It may spin faster, slower, or start to wobble in a more complex way. These changes in spin state hold clues to its internal structure, because a solid block and a loose pile of rubble respond differently to the same tidal stress. Scientists are particularly excited about what might happen on the asteroid's surface. Those same tidal forces, coupled with even slight changes in spin, are predicted to trigger asteroid quakes. Boulders may shift, fine dust may migrate, and previously buried material might be exposed. This process, sometimes called resurfacing, is one of the ways asteroids evolve over time. Usually, we can only infer it by comparing distant snapshots of many different objects. In 2029, and in the years surrounding it, we will have the rare chance to catch a single asteroid before, during, and after a strong gravitational encounter and see how its surface responds. Ground-based telescopes and radar will observe Apophis leading up to the flyby, and later the OSIRIS-APEX spacecraft will visit it up close, giving us a before and after. That is nearly unprecedented in planetary science. The 2029 event is also a crucial test of our planetary defense capabilities. Planetary defense is not about blowing up asteroids in a cinematic sense, but about finding them early, calculating their paths with high precision, and if ever necessary, nudging them slightly so they miss our planet. Apophis has already served as a training ground for the first part of that challenge, careful tracking and orbit prediction. The fly, I will put the second part under scrutiny. Because we know its orbit so well before the encounter, we will be able to compare predictions with what actually happens afterward in exquisite detail. Any mismatches will teach us where our models of gravitational interactions, small forces like thermal radiation, the Yarkovsky effect, or internal asteroid physics need refinement. That same close passage that thrills astronomers also raises an obvious question in the public mind. If it is coming inside the orbit of satellites, is there a chance it could hit one? The geostationary belt, the region where communication and weather satellites orbit at the same rate the Earth rotates, is not a solid ring. It is more like a sparse necklace of individual spacecraft, each separated by thousands of kilometers. Although Apophis's orbital path does take it through the general region where some satellites reside, the actual likelihood of a collision with any given satellite is vanishingly small. Space is still mostly empty. Nonetheless, the very geometry of an asteroid threading through our artificial environment around Earth underscores just how intertwined human technology and celestial dynamics have become. Some satellites may even detect tiny gravitational perturbations or measure Apophis's infrared emission as it passes, turning potential concern into another scientific opportunity. Another reason 2029 is such a big deal is that we are ready for it. When earlier notable near-Earth objects have passed relatively close to Earth, our observing networks were less extensive, and we often had only a modest amount of data. For Apophis, the global astronomical community has years of advance notice. Observatories around the world are planning intensive observation campaigns, from optical telescopes that will measure its brightness and track its position, to radar systems that will map its shape and surface features, to infrared instruments that will study its temperature and composition. Amateur astronomers, too, will join in, providing a flood of additional positions and light curves that help refine our understanding of its rotation and possible changes over time. The 2029 passage is not just an event, it is the centerpiece of a multi-year coordinated scientific campaign. Perhaps most importantly, the Apophis flyby creates a rare bridge between professional science and public experience. Much of astrophysics involves phenomena too distant or too faint for unaided human senses. Galaxies and exoplanets are wondrous, but you cannot see them just by stepping outside at night. Apophis changes that dynamic. Teachers will be able to tell their students, that moving point of light you see tonight, the one right there, is an asteroid, and here is what we know about it. News programs will show the predicted track across the sky for different regions. Planetariums will simulate its path and explain how we computed it. The abstract idea that asteroids sometimes come close to Earth will become concrete, anchored to a specific date, a specific object, and a visual experience people can share. There is also something philosophically powerful about watching a potentially hazardous asteroid miss us, not by accident, but by design, in the sense that we understand in advance exactly how and why it will miss. In earlier eras, a close approach like this would have gone entirely unnoticed, or at most would have been seen as a curious wandering star with no understanding of its nature or significance. In 2029, we will greet it with predictions tested to the kilometer, spacecraft ready to follow in its wake, and a global network of observers watching. That contrast between ignorance and knowledge, between helplessness and preparedness, is at the heart of why 2029 matters so much. It is a demonstration that our growing ability to read and model the cosmos is not just an intellectual achievement, but a practical shield. So the specialness of 2029 does not lie in crisis or catastrophe. Apophis will not hit us, but in opportunity. It is a rare alignment of celestial mechanics and human readiness. A sizable asteroid passes very close, yet safely. Our instruments are capable and waiting. Our spacecraft can adjust course to meet It and our society is aware enough to pay attention. In that brief passage, a chunk of primordial rock, older than any mountain on Earth, will sweep past within a cosmic hair's breadth. If we make the most of it, the knowledge we gain from the details of its orbit to the behavior of its surface will echo long after Apophis has moved on, informing how we understand both the solar system's past and our own ability to protect our future. When astronomers announced that Apophis would not hit Earth in 2029, or in any of the closely related years that once worried them, like 2036 or 2068, that conclusion rested on an intricate blend of observation, mathematics, and physics. It was not a guess, and it was not a simple draw a line and see where it goes exercise. It was the cumulative result of countless measurements, refined models, and repeated tests of our understanding of how objects move in the gravitational ballet of the solar system. The story begins with a fundamental challenge. When you first spot a new asteroid, you know almost nothing about its orbit. You might have a few images taken over a span of hours or days, showing a tiny point of light shifting against the background stars. From those early data, you can estimate an initial orbit, but the uncertainty is enormous. Instead of a single, precise path around the Sun, you get a broad cloud of possible paths that are all more or less consistent with the limited information you have. When Apophis was first discovered, that cloud of possibilities included some trajectories that intersected Earth in 2029, and thus the initial, disconcertingly high impact probability. Improving that picture is a matter of collecting more data and letting the laws of orbital mechanics do their work. Each new position measurement, each recorded point of light with a precise time and location shrinks the cloud. You can think of it like trying to infer the path of a thrown ball from a series of blurry photographs. With only 2 photos, your guess is rough. With 20 carefully timed photos, you can draw a much more specific curve. For asteroids, astronomers search not only current observations, but also archival images taken years earlier. If Apophis happened to pass through a patch of sky that someone photographed long before anyone knew it existed, those precovery images effectively extend the timeline of observations backward. The longer the orbit has been tracked, the more accurately we can project it forward. But even with excellent optical data, there is a limit to how precisely you can know an asteroid's distance and motion along the line of sight. That is where radar becomes a game changer. By beaming radio waves at the asteroid from powerful facilities like the Arecibo Observatory when it was still operational, or the Goldstone Deep Space Communications Complex, and timing how long the echoes take to return, scientists can measure its distance to within a few hundred meters and its speed toward or away from Earth to within a fraction of a millimeter per second. For Apophis, the radar campaigns in 2005, 2013, and especially 2021 sharply tightened the constraints on its orbit. What had once been a fuzzy swarm of possible future positions collapsed into a narrow track through space. This is where the concept of gravitational keyholes becomes important. When an asteroid passes near a planet, the planet's gravity deflects its path. In a simplified sense, if you know exactly how it goes by, how far from the planet's center, at what angle, at what speed, you can compute exactly what its new orbit will be. But if you are uncertain by even a small amount, say a few kilometers at closest approach, that uncertainty can blossom into thousands of kilometers difference many years later. On the mathematical target plane, that scientists used to describe close encounters, tiny regions called keyholes represent those special positions where, if the asteroid passes through them on one flyby, the altered orbit will bring it back on a direct collision course on a later pass. In the case of Apophis, early calculations showed that if it passed through certain narrow keyholes during the 2029 flyby regions, only a few hundred meters wide, It could return to hit Earth in 2036 or 2068. At the time, the asteroid's predicted path in 2029 overlapped those keyholes within the uncertainties, so scientists could not immediately rule out those impact scenarios. The key was to push the uncertainties down enough that they could say, with confidence, Apophis will miss every dangerous keyhole. That is exactly what the successive rounds of optical and radar observations allowed them to do. With each new data set, they recomputed millions of slightly different possible orbits, Monte Carlo simulations within the error margins of the measurements. For each of those virtual apophyses, they asked, does this version of the orbit hit the keyhole or miss it? As the real orbit became clearer, the fraction that hit any keyhole dropped to zero. However, gravity is not the only force acting on an asteroid. Over years and decades, a subtle effect called the Yarkovsky effect can nudge an asteroid's orbit. It happens because the asteroid absorbs sunlight and remits that energy as heat. If it is rotating, one side warms up and then radiates heat as it turns away from the sun. Those escaping infrared photons carry momentum, producing a tiny thrust. It is minuscule at any given moment, but over millions of orbits, it can move an asteroid's path by kilometers or more. Before we could be entirely sure about Apophis's future, we had to understand and measure this effect for it. Apophis, being a relatively small object with a likely rubble pile structure, is susceptible to Yarkovsky forces. Scientists needed to know its spin rate, its orientation, its size, and its surface characteristics, because all of those factors influence how it heats and cools. Years of photometric observations measuring how its brightness varies as it rotates, and radar shape modeling gave them a handle on those properties. By comparing its actual positions over many years to where it would be if only gravity acted, researchers could detect a tiny but measurable drift in its orbit attributable to Yarkovsky. Once that drift was quantified, it could be built into long-term trajectory calculations. In 2021, with the most recent radar data in hand, NASA announced that the remaining 2068 impact probability, once already slim, had effectively dropped to zero. Within the span of at least a century, Apophis is not on a collision course with Earth. Behind these conclusions lies an entire infrastructure of automated systems, like NASA's Sentry and Italy's Klaman, that continually scan updated asteroid data and recompute potential impacts. Whenever new measurements come in from a radar observation, a Gaia astrometric refinement, or a ground-based telescope, they feed into these systems, which search for any orbital solutions that might intersect Earth in the future. Apophis was once high on their risk lists, now it has been removed. The science that enabled that shift is not just about one asteroid. It is a demonstration that, given enough time and data, we can tame the apparent randomness of near-Earth objects, distinguishing those that merely visit from those that threaten. So when we say we know Apophis will miss, that knowledge rests on a deep chain of reasoning. First, that gravity and radiation forces follow predictable physical laws. Second, that our telescopes and radar can measure its motion with astounding precision. And third, that our models correctly combine all of this into reliable forecasts. The orbit of Apophis has become one of the best studied in the solar system, not because it is large or bright, but because it once carried our anxieties. In resolving them, scientists have tested and proven the tools that will protect us against whatever asteroid might appear in our future with a trajectory less forgiving than that of Apophis. When we ask, what is Apophis made of? We're really asking two things at once. First, what are its ingredients? What minerals, metals, and rocks make up this body? And second, how are those ingredients put together? Are we dealing with a single solid block or a loose pile of rubble held together by gravity? Both questions matter not only for understanding Apophis itself, but for understanding how to live safely in a solar system full of similar objects. Since we can't yet pick up pieces of Apophis and bring them into a laboratory, we rely on the light it reflects. When sunlight hits the asteroid, some of it bounces back toward us. That reflected light carries a kind of fingerprint. By splitting it into its component colors with a spectrograph, astronomers can see which wavelengths are absorbed more strongly and which are reflected more efficiently. Different minerals leave different patterns of dips and peaks in this spectrum. Using these techniques, scientists classify Apophis as an S-type asteroid, more specifically, something close to an SQ or Q-type. S stands for silicate, meaning it is dominated by rocky minerals rich in silicon and oxygen, such as olivine and pyroxene, mixed with a smaller but significant fraction of metal, mainly iron and nickel. Its spectrum closely resembles that of a particular group of stony meteorites called chondrites, meteorites low in total iron, L, and low in metallic iron, L. Again, with much of their iron locked up in silicate minerals. If you've ever seen a cut, polished meteorite with tiny chondrules, small, rounded beads of once molten rock, embedded in a lighter matrix, you have a physical analog of what Apophis's material probably looks like on a microscopic scale. Brightness measurements back this up. Apophis reflects more sunlight than the dark, carbon-rich C-type asteroids that dominate the outer belt. Its albedo, its overall reflectivity, is moderate, consistent with a relatively fresh, stony surface. That in turn hints at its history. Over time, exposure to solar wind and micrometeorite impacts space weather, an asteroid's surface, darkening it and reddening its spectrum. Apophis's spectral properties suggest that, while it has certainly aged, parts of its surface are not as heavily weathered as some older main belt asteroids. That could be because its relatively small size and active orbital environment mean its surface gets disturbed from time to time, exposing fresher material from underneath. Shape and structure are the other half of the puzzle. Radar observations, where powerful radio waves are bounced off the asteroid and their echoes analyzed, give us a crude three-dimensional picture. For Apophis, those radar images reveal an irregular, elongated body rather than a sphere. Its overall effective size is about 340 meters, but it's more like a lumpy, stretched potato than a perfect ball. Combined with how its brightness changes as it rotates, this tells us that Apophis presents different cross-sections to us over time, confirming its non-spherical, possibly bifurcated form. Whether Apophis is a solid rock or a rubble pile is a subtler question, but an important one. A rubble pile asteroid is essentially a gravitationally bound collection of boulders, gravel, and dust, with significant empty space between grains. We know from spacecraft visits like JAXA's Hayabusa missions to Itokawa and Ryugu, and NASA's OSIRIS-REx mission to Bennu, that many small near-Earth asteroids are exactly like this, astonishingly loose assemblages, often with densities significantly lower than the solid rock they're made of. That means high porosity, something like a gravel pile, not a granite boulder. Apophis's likely bulk density, inferred from its composition and comparison with similar objects, lies somewhere around 2.6 to 3 grams per cubic centimeter if it were solid rock. But many S-type rubble piles of similar composition end up with overall densities closer to 2 to 5 grams per cubic centimeter once their internal voids are factored in. While we don't yet have a direct mass measurement for Apophis, its size, spin rate, and spectral affinity with chondrite-like material all point toward it being at least moderately porous. It probably contains significant internal void space, and is held together mainly by its own weak gravity and friction between constituent rocks. Its rotation adds another clue. Apophis rotates roughly once every 30 hours, which is fairly slow compared with some small asteroids that spin every few hours or less. There is also evidence that its spin state may not be perfectly simple. It might be in a slightly excited, non-principal axis rotation, a kind of gentle tumble. Very fast rotation can tear apart a rubble pile if centrifugal forces overcome gravity and cohesion, as appears to have happened for some asteroids that split into binaries. Apophis's relatively leisurely spin is consistent with a weak, loosely bound structure that has not been spun up to the point of disruption by subtle torques like the Yorp effect, a cousin of the Yarkovsky effect, where sunlight changes an object's rotation. From a scientific standpoint, knowing that Apophis is a stony, likely rubble pile object tells us several things. First, it grounds our theories about the origin of near-Earth asteroids. Bodies like Apophis are thought to be fragments of larger parent asteroids in the main belt that were shattered by collisions. The debris from those events slowly migrates inward through gravitational resonances with Jupiter and subtle forces like Yarkovsky, eventually becoming near-Earth objects. The spectral link between Apophis and chondrite meteorites suggests that some of the meteorites that land on Earth could be chips from Apophis's siblings, or even, conceivably, from Apophis itself. In the distant past, second, composition and internal structure are central to planetary defense planning. An iron-rich, mostly solid asteroid behaves very differently from a porous rubble pile if you try to deflect it. A kinetic impactor, a space rock bumper, like NASA's DART mission used on the small asteroid Dimorphos, transfers momentum to the target. But how much of that momentum goes into changing the asteroid's path, and how much is dissipated shattering or rearranging its interior, depends on the target's structure. For Apophis, the expectation that it resembles a stony rubble pile helps scientists model what would happen if, in an alternate scenario where its orbit were dangerous, we needed to intervene. Third, Apophis's surface composition shapes what we expect to see when a spacecraft arrives. Osiris Apex, the extended mission of OSIRIS-REx, will rendezvous with Apophis after its 2029 flyby. We anticipate a surface strewn with boulders of various sizes, patches of finer regolith, and evidence of past landslides or mass movement features familiar from Bennu and Itokawa, but with its own local variations. Because Apophis is an S-type, its rocks will likely be stronger and more cohesive than the very dark, carbon-rich boulders on Bennu or Ryugu, which tended to crumble easily. When Osiris Apex uses its thrusters near the surface to stir up material, the way that material moves, whether it lofts into space, settles slowly, or barely budges, will give us a window into the mechanical properties of Apophis's regolith. Finally, the chemical makeup of Apophis connects it to the early solar system. Chondritic material is some of the most primitive rock we know, preserving records of processes that happened when the sun and planets were just forming. The minerals, the ratios of different elements, and the tiny inclusions inside chondrules all encode temperatures, pressures, and timescales from over 4-5 billion years ago. While Apophis itself has been battered, heated locally by impacts, and reshaped, the bulk composition still reflects that ancient origin. In that sense, when we ask what Apophis is made of, one answer is, it is made of the same stuff that once swirled in the disk that built the terrestrial planets, left over in small fragments that never quite grew into worlds of their own. So Apophis, beneath its dramatic name, is not exotic matter or mysterious alien metal. It is familiar, stony material silicates and metals arranged not as a monolithic mountain, but most likely as a loose, gravitationally bound heap. That combination of ordinary ingredients and complex structure is precisely what makes it so scientifically rich. It is a nearby, accessible example of the building blocks of planets and the typical architecture of small bodies, and studying it up close will sharpen both our understanding of how such objects form and evolve, and our ability to deal with them if one day we truly need to. When Apophis sweeps past Earth in 2029, our planet will do more than just watch it go by. Earth's gravity will reach out across tens of thousands of kilometers, tugging on the asteroid in ways that change not only its path around the Sun, but likely its spin and even the arrangement of rocks and dust on its surface. This is why scientists describe the encounter as a natural experiment, a real-world test of how a mid-sized asteroid behaves when it ventures deep into a planet's gravitational well. From a purely orbital point of view, what happens is straightforward in principle. In the reference frame of Earth, Apophis will follow a curved, hyperbolic path past our planet. The closer it comes and the faster it moves, the more its trajectory is bent by Earth's gravity. If you zoom out to look at the orbit around the Sun instead, this close pass effectively resets the parameters of that orbit. Before 2029, Apophis loops around the Sun in less than a year. After the flyby, its orbital period will increase to roughly 2 years. Its average distance from the Sun, its semi-major axis, its eccentricity, how stretched its orbit is, and its inclination, the tilt of its orbit relative to Earth's, will all be altered by Earth's pull. Space missions have used this gravitational slingshot effect for decades. Spacecraft such as Voyager, Cassini, and many others gained speed and changed direction by flying past planets. Apophis is essentially undergoing the same process, but as an uninvited, purely natural spacecraft. The difference is that spacecraft are rigid objects we know in detail, while Apophis is not a simple, solid body. It is an irregular, probably loosely bound asteroid that makes the encounter an experiment not just in orbital dynamics, but in the physics of deformable, granular bodies in a strong tidal field. Tidal forces are at the heart of this. Gravity gets weaker with distance. The side of Apophis that is closer to Earth will feel a slightly stronger pull than the far side. We see the same phenomenon on Earth in the rise and fall of ocean tides, driven by the Moon's gravity. On a more dramatic scale, the comet Shoemaker-Levy 9 was famously torn into pieces by Jupiter's tides in 1992, when it ventured inside the so-called Roche limit, the distance where tidal forces, Apophis will not come anywhere near Earth's Roche limit. It will remain far enough away that it will not be pulled apart. But not torn apart is a very low bar. Between no effect and catastrophic disruption lies a wide range of subtler outcomes, flexing of the interior, changes in spin, and reshaping of the surface. Numerical simulations that model Apophis as a rubble pile of thousands of particles suggest that the tidal stresses at closest approach will be strong compared with the weak gravitational and frictional forces that hold its constituent rocks together. That is especially true if its internal cohesion is low, as seems likely for many small asteroids. One prominent prediction is that Apophis's rotation will change. Right now, it spins once every few tens of hours. As it passes Earth, our planet's gravity will exert a torque, a twisting force on the irregularly shaped body. Because the asteroid is not a perfect sphere, the gravitational pull is not evenly distributed. Some parts stick out more, some less. This asymmetry, combined with the changing direction of Earth's pull during the flyby, can alter the asteroid's spin rate and tilt its spin axis. After 2029, Apophis may end up rotating faster or slower, and its pull may point in a different direction in space. Such changes are not merely curiosities. An asteroid's spin state influences how it experiences the Yarkovsky and Yorp effects, tiny radiation forces that over long timescales can significantly alter its orbit and rotation. By measuring Apophis's spin precisely before and after the encounter, scientists can test models of tidal torques and improve predictions for how close planetary flybys can reorient small bodies. We have hints of such processes from other near-Earth asteroids that have passed repeatedly near Earth, but Apophis gives us a rare chance to predict a spin change in advance and then check Prediction with direct data. Perhaps the most visually striking effects of Earth's gravity will occur on the surface. If Apophis is indeed a rubble pile, its boulders and regolith are in a delicate balance. The combination of changing tidal forces and even small adjustments to spin can disturb that balance. Boulders perched on slopes may shift downslope. Fine dust may migrate from one region to another. Entire patches of the surface could experience landslides or subtle slumping. These asteroid quakes may not be violent in the way we think of earthquakes, but on a low-gravity body they do not need to be. Even tiny accelerations can set material in motion. Laboratory experiments and computer simulations of granular materials in low gravity suggest that such shaking can cause size sorting, the so-called Brazil nut effect, where larger particles rise relative to smaller ones when a mixture is vibrated. If that happens on Apophis, we might see patterns where big boulders end up clustered in certain areas and finer material collects elsewhere. Over many such encounters across an asteroid's lifetime, tidal interactions could be a major driver of how its surface evolves, refreshing it by bringing buried material to light and smoothing or roughening different regions. The crucial test of all these ideas will come from observations. In the years leading up to 2029, astronomers are building an increasingly detailed baseline picture of Apophis's orbit, shape, spin, and surface properties using optical telescopes, infrared data, and radar imaging. These before measurements are essential. Without them, we would not know how much anything has changed after the flyby. Then, in the months and years following closest approach, we will collect the after data. Earth-based telescopes will track the asteroid's new orbit with high precision, confirming the predicted increase in orbital period and any subtler changes in eccentricity and inclination. Light curve measurements will reveal any alteration in rotation rate or pole orientation. Radar can once again probe its shape and spin, providing an independent check. Most excitingly, the OSIRIS Apex spacecraft will rendezvous with Apophis not long after the flyby. From close range, it will map the asteroid's surface at resolutions impossible from Earth, looking for signs of recent disturbance, fresh fractures, boulder tracks, small craters that look sharper than their surroundings, or areas where fine dust has been stripped away or newly deposited. By comparing these observations with pre-flyby shape models and global maps, scientists hope to identify exactly where and how the asteroid responded to Earth's tidal pull. Together, all this turns Earth from a passive bystander into an active part of the experiment. Our planet's gravity is not something we control, but it functions here as a natural tool, an invisible lever that perturbs Apophis in ways we can predict and then verify. The better our models match reality, the more confidence we can have when applying those same models to other asteroids that might one day pose real danger. In that sense, the 2029 encounter is a rehearsal, not for a disaster, but for understanding and, if ever needed, manipulating the trajectories and behaviors of small bodies in our neighborhood. Apophis will leave the encounter on a new path with a subtly reshaped spin and perhaps a freshly rearranged surface. We will be watching closely, using Earth's gravity as a probe to reveal what an asteroid is really like under stress, knowledge that will outlast this single flyby and shape how we think about countless other rocks that share our solar system. When OSIRIS-REx launched in 2016, its job description was clear and finite. Go to the near-Earth asteroid Bennu, study it in detail, grab a sample, and bring that sample back to Earth. In 2023, when the return capsule streaked into the Utah desert carrying material from Bennu's surface, that mission was, in one sense, complete. But the spacecraft itself was still healthy, still equipped with cameras, spectrometers, and propulsion, and still cruising through the inner solar system. Rather than retire a perfectly capable spacecraft, NASA decided to give it a new assignment, one perfectly tailored to the unique opportunity that Apophis presents in 2029. That is how OSIRIS-REx became OSIRIS-APEX, the Apophis Explorer. Reusing OSIRIS-REx for Apophis is a kind of scientific judo, turning what we already have to maximum advantage. Designing, building, and launching a new spacecraft is incredibly expensive and time-consuming. Here, we already have a flight-proven craft, one that has navigated to and operated in the delicate low-gravity environment of a rubble pile asteroid. The mission team knows how its systems behave, how its instruments perform, and how to fly it close to a small body without incident. That experience is invaluable when approaching Apophis, which is similar in many ways to Bennu, but arrives with the added twist of having just undergone a close encounter with Earth's gravity. The choice of Apophis as the next target is not arbitrary. Among the many near-Earth asteroids, Apophis stands out precisely because of its 2029 flyby. Earth-based telescopes and radar will characterize Apophis in the years leading up to that date, giving us a detailed before picture its orbit, rotation, shape, and surface properties as seen from afar. Then Earth's gravity will perturb it, potentially changing its spin and causing subtle reshaping of its surface. OSIRIS-APEX will arrive afterward, providing the crucial after picture from close range. Few other asteroids offer such a clean, time-linked experiment in how a planetary flyby affects a small body. After releasing the Bennu sample capsule toward Earth, the spacecraft performed a divert maneuver so it would not follow the capsule into the atmosphere. Instead, it entered a new solar orbit, conserving fuel for its journey to Apophis. The extended mission plan is to guide OSIRIS-APEX onto an intercept trajectory so that it can rendezvous with Apophis shortly after the asteroid's 2029 close pass. Once there, the spacecraft will not just fly by, it will go into orbit around Apophis and stay for roughly 18 months, circling a body barely a few hundred meters across in an environment where gravity is tens of thousands of times weaker than on Earth's surface. The spacecraft will carry essentially the same suite of instruments that served it at Bennu to the extent they remain operational: high-resolution cameras for detailed imaging, spectrometers that can read the chemical signatures in reflected sunlight and emitted thermal radiation, and a laser altimeter to map the asteroid's shape and topography. These tools are well suited to Apophis. At Bennu, they revealed boulder-strewn landscapes, measured temperature variations across the surface, and produced precise 3D models that let scientists infer the asteroid's internal density structure. At Apophis, they will be used in similar ways, but with an added layer of comparative science. How does Apophis, with its different composition and dynamical history, resemble or differ from Bennu? One of OSIRIS-APEX's primary goals is to measure Apophis's mass, and by combining that with its volume, its bulk density, the spacecraft can do this indirectly by tracking tiny changes in its own trajectory as it orbits, caused by the asteroid's gravity. A lower density than solid rock would confirm that Apophis, like Bennu, is a rubble pile filled with internal voids. Knowing the density and how it varies from place to place will tell us a lot about its internal structure, whether it is a uniform aggregate of similar-sized blocks or a more complex assemblage with denser cores and lighter outer layers. That, in turn, feeds into models of how such asteroids form from collisional debris and how they respond to stresses, natural or human-induced. Another key objective is to look for signs of surface change linked to the 2029 encounter. By the time OSIRIS-APEX arrives, Earth-based observations will have already tracked any significant alteration in Apophis's spin rate or pole orientation. From close up, the spacecraft can go further, examining the landscape for fresh landslides, exposed patches of less weathered material, shifted boulders, or small new craters created by loosened rock falling or rolling downslope. Detecting and mapping such changes will help confirm and calibrate our models of tidal resurfacing, putting hard observational constraints on how much shaking a close flyby actually causes. Osiris Apex will also perform an especially intriguing experiment, using its own thrusters to deliberately disturb Apophis's surface. By flying very low over selected regions and firing its attitude control jets, the spacecraft can stir up the regolith, loose surface material, just as OSIRIS-REx's sampling maneuver did at Bennu. Now, with the express purpose of studying how that material moves, cameras and spectrometers will watch how dust and small pebbles rise, drift, and settle back in the asteroid's microgravity. This will give direct insight into the mechanical properties of Apophis's surface, how cohesive it is, how easily it flows, and how grains of different sizes segregate or mix. Such information is vital to understanding not only Apophis, but any mission that might one day need to anchor to, push, or otherwise interact with a small body. All of this has clear implications for planetary defense. Apophis is a representative of the population of potentially hazardous asteroids that cross Earth's orbit. The physics that govern its behavior under tidal stress, or when its surface is disturbed, are the same physics that would apply to any similar object we might have to deflect in the distant future. By using Osiris Apex to ground truth, our models testing predictions against detailed, real-world data, we improve our ability to forecast how a deflection attempt would alter not just an asteroid's trajectory, but its internal and surface structure. Do kinetic impacts risk fragmenting a rubble pile? How efficiently is momentum transferred? How does regolith behavior affect where a spacecraft can safely operate? Osiris Apex will not test deflection directly, but it will refine the underlying science that makes deflection planning reliable instead of speculative. There is also a broader scientific payoff. Bennu and Apophis together form a kind of controlled comparison, two near-Earth asteroids of similar size but different compositions and orbital histories, each studied up close by the same spacecraft with the same instruments. Differences between them can be more confidently ascribed to genuine physical contrasts rather than quirks of measurement. That comparative approach will sharpen what we can infer about the entire near-Earth asteroid population from remote observations alone. When future telescopic surveys discover yet another small, dark point of light on a near-Earth trajectory, we will be better able to interpret its spectrum, light curve, and orbit by analogy with what we have learned from Bennu and Apophis. In the end, Osiris Apex represents a smart, economical way to turn a completed mission into a new frontier. It leverages the success at Bennu to meet Apophis at a uniquely revealing moment in its journey, transforming a one-off sample return into a broader program of asteroid exploration and planetary defense research. As Apophis swings past Earth in 2029, millions of people may watch it as a moving dot of light. Osiris Apex will be preparing to join it, turning that transient spectacle into years of close-up investigation and helping us understand not just that this particular asteroid will miss us, but how to live with all the others that share our part of the solar system. Long before Apophis was discovered, scientists understood in a general way that asteroids sometimes hit planets. The craters on the Moon, the extinction of the dinosaurs, and the occasional meteor events in recent history all testified to that fact. But for much of the 20th century, the idea that we could systematically find, track, and even prevent dangerous impacts belonged more to theory and science fiction than to organized practice. Apophis changed that by turning an abstract risk into a concrete, time-stamped question. What if this one hits? What can we actually do? When Apophis first showed a non-trivial chance of impact in 2029, it caught planetary scientists in the midst of building the first serious surveys for near-Earth objects, such as Linear and later Pan stars and Catalina. Those efforts were already finding thousands of asteroids, but Apophis highlighted the stakes and the gaps. It was large enough to cause regional devastation, and it was discovered only 25 years before its near miss. That is plenty of time to refine an orbit and, in principle, even to mount a deflection mission, but only if you already have the systems in place to detect it, assess it, and respond. One of the most immediate lessons Apophis drove home was the need for robust, continuous sky surveys specifically tailored to find potentially hazardous objects. In the 1990s, the U.S. Congress had asked NASA to discover 90% of near-Earth asteroids larger than 1 kilometer. That spaceguard goal was largely met, but Apophis, at roughly 340 meters across, was significantly smaller than that threshold, yet dangerous enough to demand attention. Its discovery added urgency to the push for a second goal, finding at least 90% of near-Earth objects 140 meters and larger. That shift in size focus was crucial. It acknowledged that civilization-ending impacts from multi-kilometer bodies are very rare, while regional-scale impacts from 100-meter asteroids are more frequent, and in many ways, more actionable if we find them early. Equally important was the realization that discovery is only the first step. Apophis entered public conversations with dramatic headlines, largely because the early impact probability was both unusually high and genuinely uncertain. That uncertainty was not a failure of science. It was an accurate reflection of how little was known from the first handful of observations. But it made clear that the public, policymakers, and media all needed a better framework for understanding impact risk and its evolution as new data came in. This is where tools like the Torino scale, and later the Palermo scale, came into sharper focus. The Torino scale provides a 0-10 rating that combines impact probability and potential energy into a single, color-coded number intended for public communication. Apophis briefly reached Torino level 4, the highest rating any known asteroid has ever had. Watching that rating rise, then fall back to 0 as additional observations ruled out impact, taught scientists and communicators how crucial it is to explain that these numbers are not static verdicts but dynamic assessments. They change as our knowledge improves. Apophis became a case study in why initial alarm does not necessarily mean ultimate danger, and why patient data gathering is the correct response. Behind those public-facing scales sits a far more complex computational apparatus. Systems like NASA's Sentry and ESA Klamen continuously ingest updated orbital data for thousands of near-Earth objects, propagate their orbits forward in time, and flag any that have a non-zero chance of hitting Earth in the next century or so. Apophis was one of the first asteroids to seriously exercise these systems. Each time new radar or optical measurements arrived, its orbit was refitted, its future paths recalculated, and its impact probabilities updated automatically. That process revealed not only where Apophis would and would not go, but also where the software and models themselves needed refinement. In that sense, Apophis served as a real-world test of the entire impact monitoring pipeline. Another major lesson Apophis drove home concerned the subtler forces that affect asteroid motion, especially the Yarkovsky effect. Before Apophis, the Yarkovsky effect was well known among specialists as a theoretically important phenomenon that could, over long times, nudge small bodies into new orbits. But Apophis's long-term impact probabilities for later dates, such as 2068, depended sensitively on this tiny thermal thrust. That forced scientists to treat Yarkovsky not as a background curiosity, but as a primary ingredient in orbit prediction for potentially hazardous asteroids. The effort to measure and model it accurately in Apophis's case sharpened our general understanding of how sunlight and heat alter asteroid paths. That understanding is now standard in serious planetary defense calculations. Apophis also played a more subtle role in shaping institutional responses. The prospect, even temporary, of a non-negligible impact probability spurred coordination between NASA, international partners, and agencies responsible for emergency management. It helped motivate the formal creation of NASA's Planetary Defense Coordination Office, PDCO, which now serves as the focal point for finding, tracking, and characterizing potentially hazardous objects, as well as for planning response strategies. Internationally, organizations like the United Nations Committee on the Peaceful Uses of Outer Space, COPUOS, strengthened working groups on near-Earth objects, recognizing that any serious impact threat would be a global issue, not a purely national one. We can see Apophis's influence echoed years later in missions like NASA's DART and ESA Hera. DART, which deliberately crashed a spacecraft into the small moon Dimorphos in 2022 to test kinetic impact deflection, was not designed because of Apophis specifically, but it drew on the broader realization crystallized in part by Apophis that we must move from theoretical deflection strategies to tested techniques. Apophis had shown how quickly a newly discovered asteroid could move from obscurity to object of concern. That timeline leaves little room for improvisation. By the time another Apophis-like object is found on a more dangerous trajectory, we will need proven options on the shelf. DART's successful demonstration and Hera's planned follow-up measurements are the direct descendants of that mindset. Another lesson lies in public perception and education. When Apophis first hit the news, some coverage veered towards sensationalism, emphasizing doomsday scenarios despite scientists' repeated cautions about uncertainty and the likelihood that further measurements would rule out impact. Over time, as predicted, the risk estimates did drop to zero. That experience gave scientists and communicators a live example to use in explaining how asteroid risk assessment works, why early odds can sound alarming, why those odds almost always change, and why we don't know yet is a legitimate and often reassuring answer. Educational outreach around Apophis has since helped people understand that the real story is not "we are doomed" or "we are safe," but rather we are becoming able to know which is the case decades in advance. Finally, Apophis has contributed to a quiet but important cultural shift, the idea that asteroid impacts are not purely acts of fate. The close study of its orbit, the ruling out of impacts in 2029, 2036, and 2068, the plans to visit it with OSIRIS APEX after its flyby, all of these reinforce the message that we are no longer passive in the face of celestial hazards. We cannot move planets, but we can find, track, and, if needed, gently redirect small bodies. Apophis began as a symbol of randomness and chaos. It has become instead a symbol of how systematic observation and international cooperation can turn a potential threat into a scientific opportunity. In that transformation lie the deepest lessons for planetary defense. We learned that we must survey the skies continuously, that we must model orbits with all relevant physics, that we must build institutions ready to coordinate a response, and that we must communicate risk in a way that is honest about uncertainty yet calm and constructive. Apophis, the once worrisome point of light, has become a kind of benchmark against which we measure our readiness. The fact that we can now say, with confidence, that it poses no danger for at least a century is not just a statement about one asteroid. It is evidence that planetary defense has matured from a speculative idea into an emerging capability, one that will shape how we live with the countless other small worlds that share our space around the sun. Apophis has become one of the clearest milestones in the history of planetary defense because it forced almost every part of the system discovery, tracking, risk analysis, international coordination, even public communication, to be tested in a realistic way. When it was discovered in 2004, and initial calculations showed about a 1 in 37 chance of impact in 2029, that number instantly exposed both what we already could do and what we still lacked. On the plus side, the fact that we even knew about a 340-meter asteroid 25 years before a close approach was a sign that early survey efforts were working. Projects like Linear and Catalina were beginning to find many near-Earth objects. But Apophis also revealed that our surveys were far from complete, especially for objects a few hundred meters across, large enough to devastate a region, but small enough to slip past less thorough searches. That realization helped shift policy. The original Space Guard goal pushed NASA to find 90% of NEO larger than 1 kilometer. Apophis, well below that size but still dangerous, contributed to the political momentum behind a new mandate: find at least 90% of near-Earth objects 140 meters and larger. This, in turn, underpinned investment in better surveys, upgrades to ground-based search programs, plans for space-based infrared telescopes like NEO Surveyor, and support for wide-field facilities such as the Vera C. Rubin Observatory, whose legacy survey of space and time LSSD will dramatically expand our catalog of small, faint asteroids. Apophis also stress-tested how we assess risk once an object is found. Early on, the handful of observations yielded a wide cloud of possible future orbits, some of which intersected Earth. As more data came in, that cloud shrank and the impact probability dropped. This evolution was expected by specialists, but to the public it was confusing. People read one day that there was a real impact chance, and later that the risk had disappeared. Apophis showed very clearly that risk probabilities for newly discovered objects are not final verdicts. They are snapshots that change as information improves. That pushed agencies and scientists to refine the tools and language they use. The Torino scale, intended for public communication, was suddenly on display because Apophis briefly reached level 4, a close encounter with a 1% or greater chance of a collision capable of regional devastation, watching it then step back down to 0 as new measurements were incorporated illustrated both the usefulness and the limitations of a single number scale. It highlighted the need for careful explanation. A high Torino rating is a reason to gather data and refine the orbit, not to panic. A later drop to 0 means the earlier concern has been resolved. Not covered up, behind the Torino and Palermo scales, automatic impact monitoring systems such as NAS, as Sentry, were put through their paces. Every time new positional or radar data on Apophis arrived, Sentry recomputed its orbit and scanned for any possible future Earth impacts over the next century. That process used sophisticated algorithms to propagate thousands of slightly different orbital solutions forward in time, accounting for uncertainties. Apophis, with its initially worrisome probabilities and later dismissal, became one of the first high-profile tests of this entire chain, from data intake to risk reporting. Weak points in the software, in how uncertainties were modeled, and in how subtle effects like the Yarkovsky effect were included, became obvious and were improved. That legacy lives on today in upgraded systems such as Sentry Roman 2, which uses more advanced methods to handle complex gravitational interactions. The Yarkovsky effect itself is another area where Apophis left a mark. This tiny force, caused by uneven thermal re-radiation of sunlight, can gradually shift an asteroid's orbit. For most large objects and short timescales, it is negligible, but for decades-long predictions of few hundred-meter asteroids, it matters. Apophis's longer-term risk assessments, particularly for dates like 2068, depended on how strongly Yarkovsky was pushing it. That forced scientists to measure the effect on Apophis directly by comparing its observed motion over many years to purely gravitational predictions. As they did so, they sharpened techniques to infer surface properties, spin, and thermal behavior from small orbital drifts. Today, serious impact studies routinely include Yarkovsky, in part because Apophis demonstrated that ignoring it can leave a small but consequential uncertainty in long-term forecasts. Institutionally, Apophis helped galvanize planetary defense as a recognized, organized field rather than a loose collection of interested scientists. The realization that a significant asteroid could emerge from near obscurity to a non-negligible impact risk, then be cleared only after intense work, emphasized that dealing with such events could not be purely ad hoc. NASA's Planetary Defense Coordination Office, PDCO, established in 2016, grew out of this awareness. The PDCO is now responsible for overseeing NEO searches, maintaining impact assessment capabilities, and coordinating with other U.S. and international agencies if a serious threat is found. Apophis was often cited in discussions that led to its creation as a near miss that we handled well scientifically, but that made clear we needed formal structures in place for any future object. That didn't miss. Internationally, Apophis spurred cooperation through bodies like the International Asteroid Warning Network, ION, and the Space Mission Planning Advisory Group SMPAG, both recognized by the United Nations. These groups share observational data, compare impact monitoring results, and explore response strategies. If an Apophis-like object were on an actual collision course, decisions about warning, evacuations, or even mounting a deflection mission would cross national boundaries. Apophis showed this isn't hypothetical. It's only a matter of time before another object with concerning odds appears. Establishing protocols now who informs whom, what thresholds trigger action, was one of the indirect but important consequences of Apophis's brief time on risk lists. There is also the technological aspect. Apophis didn't require a deflection mission, but it underlined the need to have tested methods ready before they are urgently needed. That logic supports missions like NASA's DART, which in 2022 successfully changed the orbit of Dimorphos, and ESA Hera, which will follow up with detailed measurements of the impact outcome. While Apophis was not the direct target of these missions, it was one of the clearest public examples used to justify moving from theory to experiment. The question became, if Apophis or a similar object were found on a collision path, would we want our first attempt at deflection to be improvised? The answer was no, and that helped turn planetary defense from a paper exercise into hardware on a launch pad. Finally, Apophis has shaped how scientists talk with the public about asteroid threats. Its story, initially alarming odds, then systematic data-driven resolution, and now a close but safe 2029 flyby, provides a concrete narrative that can be used in classrooms, documentaries, and policy briefings. It allows experts to say, here is how the process works in practice, and here is why early headlines changed as we learned more. That narrative helps build trust. People can see that the system does not just declare danger or safety arbitrarily, but updates its conclusions transparently as new evidence comes in. In all these ways, Apophis has been a kind of dress rehearsal on a real stage. It showed that we can discover a dangerous-looking object in time, that we can refine its orbit until we know whether it will hit or miss, and that we can use that process to strengthen our tools. Institutions and communication. The fact that Apophis itself turned out to be harmless, at least for the foreseeable future, is almost beside the point. Its most enduring contribution is that it pushed planetary defense from an idea into a functioning capability, giving us a clearer sense of what it will take to handle the next Apophis, especially if that one is not just passing by.